Hello, and a warm welcome to this Gresham College lecture on neutrinos, the particles that should not exist. Some of you might remember the great impression that was made a few years back by an announcement entirely unexpected made at CERN on September 23rd, 2011. At that time, the physics world was shocked when Professor Antonio Reditato presented new results from a particle physics experiment he was heading called OPERA. The experiment depicted here consisted in measuring a beam of particles that had been produced at the particle physics nuclear laboratory at CERN in Geneva and sent through the crust of the Earth to Italy near L'Aquila under the Gran Sasso mountain, where a detector was located to pick up those particles after they traversed the Earth for a length of about 730 kilometers. The particles traveling at the speed of light ought to have taken 2.4 microseconds to do the journey. But after 2 years of hard work and all possible checks, the experiment in L'Aquila had found that some of the particles arrived earlier than predicted, a full 60 nanoseconds earlier than they should, which meant that those particles were traveling faster than the speed of light, 7 kilometers per second faster. Now, this announcement was absolutely shocking because, of course, the speed of light is a barrier that cannot be broken according to Einstein's theory of special relativity and general relativity. And so this new finding, if true, would have revolutionized our understanding of physics, and indeed the media all over the world picked it up with headlines such as, "Does it mean time travel is possible?" Other experiments rushed to verify the claim, and in the meantime, theoretical physicists went back to their drawing boards trying to come up with possible explanations for this effect. The OPERA collaboration posted an article on a website before peer review so that the physics community could scrutinize the claim and help find any possible flaws. In the short space of 3 months, that paper was cited over 200 times and over 100 blog posts were written about it. Perhaps the physics community would have been better served at that point to remember the so-called Pauli effect, named after the great physicist and founder of quantum mechanics Wolfgang Pauli, whom Albert Einstein considered his intellectual heir. Now, the Pauli effect is not to be confused with something else entirely, namely the Pauli exclusion principle, which is actually a physics principle that is very well known, very well understood, and it's entirely real. The Pauli effect is a little bit of a tongue-in-cheek, actually, if you like, story circulating about Pauli himself, who, it was reported, was the bearer of an uncanny effect. Every time Pauli visited an experimental lab from the 30s onward, it was reported that some laboratory equipment stopped working. And this was circumstantiated enough that the great experimental physicist Otto Stern asked Pauli not to come and visit him in his lab in Hamburg anymore for fear that Pauli would bring with him this cloud of equipment failure that allegedly always accompanied him. In fact, it is reported that in 1950, when Pauli was visiting Princeton, the cyclotron accelerator at the university broke down and actually burnt down entirely. So maybe, is it possible that the physicist whose idea first introduced the notion of neutrinos, the kind of particles that the OPERA experiment was measuring, is it possible that Pauli himself was haunting the OPERA experiment and causing this strange effect, this malfunctioning perhaps of the apparatus of detection? Well, it turns out that in June 2012, 9 months after the shock announcement, the very same scientists responsible for the experiment discovered that a faulty cable was indeed to blame for the faster-than-light measurement. In the meantime, other experiments had disputed the claim and found the neutrinos to travel exactly the speed of light, and so did OPERA. So neutrinos slowed down to the speed of light. Professor Reditato resigned his post. So those neutrinos, those particles that OPERA said were initially traveling faster than light and then weren't, were the brainchild of Wolfgang Pauli, whom you see on this slide on the occasion of his 45th birthday, celebrating in April 1945 in Zurich at the ETH, where he was working. You see him in the central picture studying and working with Albert Einstein in 1926. Now, the story of neutrinos begins with Pauli in 1930, when he was greatly puzzled by the mystery of a radioactive process called beta decay. At that time, it had been observed that certain unstable radioactive elements were spontaneously changing, transforming into a different element, and in the process they were emitting a negatively charged particle called the electron. Now, the electron had been measured to have a range of kinetic energies, which is depicted in the figure on the right by the red curve. So there was a spread of possible energies for the electron, but that greatly puzzled physicists, including Pauli, because whatever process was at work inside the atomic nucleus from which the electron was coming, if there was a certain amount of energy at disposal of the electron, and the electron carried away that energy, well, some electrons obviously had more of that energy than others, and so normally you would expect actually that all of the electrons would carry away the same amount of energy, which is depicted by the blue line in the plot. But that was clearly not the case, and so the question was, where did the rest of the energy go for the electrons that carried away less than the maximally possible energy? Now, Niels Bohr, he of quantum theory fame, one of the founding fathers of quantum mechanics, went as far as saying that, in his opinion, the fundamental principle of conservation of energy had to be abandoned. Pauli hit on a different idea, a different remedy, which he called a desperate remedy. And he was very conscious that this was bound to be controversial, and so he floated the idea first, informally, in a letter to a group of his friends called the radioactive friends, working in Tübingen, a university town some 200 kilometers north of Zurich, where Pauli lived and worked at the Swiss Federal Institute of Technology. In his letter in December 1930, Pauli proposed a desperate way to escape from the problems of the continuous beta spectrum in order to save the law of energy conservation. So he postulated that inside the nucleus lurked a new particle, light and neutral, and that this particle, which was not being detected, was responsible for carrying away the additional energy that the electron was missing. So the missing energy, according to Pauli, was taken away by this unseen particle that he called the neutron. Now, this is not the neutron that we know today, as we shall see, because remember, at that time, the only known particles were the proton, the positively charged component of the nucleus, and the negatively charged electron. And so to introduce a new neutral particle at that time was indeed quite a bold, quite desperate step for a theoretical physicist like Pauli. 2 years later, James Chadwick announced in a Nature paper that he had discovered the neutral, what we actually call the neutron today, a heavy neutral particle that sits inside the nucleus. This was not the same particle that Pauli had in mind, and so Pauli's hypothetical particle was in need of a new name. And this new name was supplied by the great Italian physicist Enrico Fermi, who in 1934 worked out a new theory to explain the existence of this particle, which he called the neutrino. And this was a wordplay in Italian, because in Italian the suffix ino means the small one, as opposed to the suffix one, which means the big one. And so Enrico Fermi thought it appropriate that since the neutron, or neutrone in Italian, had already been discovered by Chadwick, then this new particle, which was due to be also neutral but also much lighter, should be called neutrino, the small one. And so Fermi also worked out that the neutrino and the electron are not inside the nucleus during beta decay. They're actually produced as part of the decay process, differently from what Pauli thought. But now with the neutrino, and as Fermi worked out, it was possible to explain quantitatively the shape of the spectrum that we observe, and in so doing, save at the same time the principle of conservation of energy, as well as explain the experimentally observed distribution of energies. So a new branch of physics was born at this point, what we call now the physics of weak interactions, which over time since then would give rise to no fewer than 10 Nobel Prize for Physics. Unfortunately, none of them were women yet, but hopefully this will change in the future. As the theory of weak interactions was being worked out, it became clear why neutrinos had not been observed before, namely because they were extremely difficult to see, as they were only subject to the so-called weak interaction, one of the four fundamental forces, and one that only works on very, very small scale. Indeed, it reaches distances which are 100 times smaller than the size of a nucleus, and on that scale, the weak force is 100,000 times weaker than electromagnetism. So here's what we know today about how the weak force works and the beta decay process that so much puzzled Pauli works. Here's a picture of a carbon atom, sort of a high school diagram. This is not entirely correct. It's not the picture that we now know quantum mechanically is appropriate, but nevertheless it will do for the purpose of explaining beta decay. So the atom is constituted by a nucleus at the center and a cloud of electrons, in the case of a neutral carbon atom, 6 electrons going around it. This picture is not to scale. Remember, the nucleus is much, much smaller than the atom. In fact, the vast majority of the volume of the atom is empty. Inside the nucleus, we find protons, which are positively charged, and neutrons, which are the neutral particles that Chadwick discovered. Now, a carbon atom has got 6 protons and 6 neutrons, and it is the number of protons that determines the chemical element, in this case, the carbon atom. But you can also add additional neutrons on top and still retain the same element. In this case, the carbon-14 atom has got the same 6 protons as a carbon-12, but it's got 8 neutrons, bringing the total number of nucleons to 14. Now, the carbon-14 atom is radioactive. It's unstable with a decay time of 5,700 years, which is the basis on which radioactive or radio dating of fossils, for example, is based on. By measuring the amount of leftover carbon-14 atoms, we can date objects and fossils and other elements from the past. Now, what happens during beta decay is that inside this carbon-14 atom, one of the neutrons decays into a protons with over the timescale of 5,700 years on average. And in particular, what happens is that the neutron gets transformed in its constituents. The neutrons and protons themselves are not fundamental particles. They are composite particles which are made of quarks, and the quarks lurking inside the neutron are 1 up quark and 2 down quarks, and in the beta decay process, through the weak interaction, one of the down quarks gets transformed into an up quark, as you can see in the bottom diagram, and that transforms the neutron into a proton, and in the process an electron is produced and an anti-neutrino, to be specific, an electronic anti-neutrino. That is the fundamental physics, the particle physics, that explains the beta decay process that Pauli was so interested in. Now, at that time, in the 1930s, theoretical physicists concluded that to detect these neutrinos was experimentally impossible because they were so weakly interacting and so difficult, therefore, to see in any possible way. But in the 1950s, physicist Fred Raines took it upon himself to achieve the impossible, to measure the existence of the neutrino particle, and later he would say that he did so simply because everybody said you couldn't do it. So Raines had been working with Richard Feynman on the Manhattan Project in Los Alamos, and so he knew a thing or two about radioactivity and nuclear physics. And initially, in 1950 or 1951, had the idea of trying to measure neutrinos by measuring the copious flux of neutrinos produced during an atomic explosion. So his slightly madcap project initially was to take a neutrino, to build a neutrino detector and to bury it 40 meters away from an atmospheric nuclear atomic explosion that was being done as a test in near Los Alamos, and let the detector fall freely through a vacuum tube and then land at the bottom in what his diagram helpfully labels as feathers and foam rubber. Now, this was a potentially viable way of measuring neutrinos, and in fact, when Raines talked to or sent a letter to Enrico Fermi about his plans, Fermi wrote back that he was very interested in this idea, and in fact, he was very interested in seeing how your 10 cubic feet scintillator counter, the particle detector that Raines wanted to use, is going to work. But I do not know of any reason why it shouldn't. But before Raines had the opportunity to carry out his project, which had been approved by the competent authorities, he met another physicist in Los Alamos, Clyde Cowan, and together they decided to change tack, and instead of using an atomic bomb, they switched to using a perhaps slightly more pacific mean of detection, namely a nuclear reactor. So they installed a neutrino detector that they had designed next to a nuclear power plant at Hanford, Washington, a power plant that was designed to produce tritium and plutonium for nuclear weapons. And in the process, this power plant would produce a great deal of antineutrinos. More precisely, would produce a flux of 10,000 billions antineutrinos per second per centimeter squared. So Raines and Cowan put two large water tanks, 400 liters of water, next to the nuclear reactor, and they hoped to catch one of those 10,000 billion neutrinos per square centimeter per second. As the antineutrino came out of the detector, it would hopefully strike a proton inside the water tank. That proton would be converted into a neutron and into a positron, which is the antiparticle corresponding to the electron. And since the positron is a piece of antimatter, it would annihilate almost immediately in water, and the signature of that annihilation would be two particles of light, two photons, high energy photons, being emitted back to back in opposite directions. The neutron would also be absorbed shortly afterwards, and in the process emit another particle of light, another photon that they could also detect. And so the signature for a neutrino, or rather an antineutrino, being captured by the tank of water was a couple of back-to-back photons, 180 degrees apart, and followed a little bit later by another photon coming from the neutron. So they set off with this experiment. The first version didn't quite work because the site wasn't suitable. So in time they moved it to a different site in South Carolina under more favorable conditions. And in 1956 they announced the detection of the neutrino after having seen reliably an average of 3 events per hour for a number of months. They had managed to catch what Raines would later describe as the most tiny quantity of reality ever imagined by a human being. So this was just the beginning of a journey of discoveries over the years, during which the neutrino would crop up over and over again. It would crop up in a number of mysteries of fundamental physics, but it would also help us clarify and clear up some mysteries, as we shall see. So the kind of neutrino that Raines and Cowan had seen was the electronic neutrino, or rather the electronic antineutrino, the one that Pauli had postulated so long ago, and over time it became clear there were other types of neutrino as well. So the so-called leptons family is made of the electrons and of the muons, which is another version of the electron but about 200 times heavier, which is unstable. We also have the tau lepton, which is 3,500 times heavier than the electron, and it's equally unstable. And each one of those 3 particles has got its own neutrino and its own antineutrino: the electronic neutrino, the muon neutrino, and the tau neutrino. So 3 families of neutrinos that were discovered first in 1956 by Raines and Cowan. The muon neutrino was discovered in 1962, while the tau neutrino had to wait until 2000. So this was the beginning of a very exciting road of discovery of new physics that would take us all the way to very, very distant places in the universe, using a particle that was once thought to be completely undetectable to advance the frontiers of knowledge of fundamental physics. Very quickly, neutrinos started cropping up everywhere nuclear reactions were present. For example, the sun is powered by nuclear fusion in its core, and this process of nuclear fusion produces a large amount of electronic neutrinos. Two of the most important processes that produce neutrinos in the core of the Sun are the proton-proton fusion, which produces deuterium, a positron, and a neutrino, and the process that transforms a boron atom into a beryllium atom, a positron, and a neutrino. All of this goes on in great quantities inside the Sun, and that produces a flux of neutrinos, of which about 10 billions per second reach the Earth. And so the idea would be that if we could measure these neutrinos, we would be able to learn more about the nuclear reactions that go on inside the Sun that we cannot otherwise see. The neutrino takes about 2 seconds to travel through the Sun unimpeded, while a photon produced by the same nuclear reactions at the center of the Sun would take of the order of 100,000 years to get to the surface, because it keeps being scattered by the dense plasma inside the Sun. So in the 1950s, Raymond Davis started putting together a detector to see these solar neutrinos. He created a tank that was buried in the Homestake gold mine in South Dakota, and it filled it with about 500,000 liters of a chlorine-based dry cleaning fluid. The idea being that one of the electronic neutrinos coming from the Sun, when it hits the chlorine atom inside the tank, it would transform that atom into a radioactive argon atom that could then be flushed out when carefully filtering the chlorine of the detector. Now, make no mistake, this was a very difficult experiment to make. Davis expected about 20 argon atoms per month out of the gazillion atoms that were inside this 500,000 liters of chlorine inside the detector. And this was grueling, difficult work. The detector was placed at the bottom of the mine to protect it from interference from other particles, for example, cosmic rays and so on. And it was 90 degrees Fahrenheit inside the mine, so it was really hard to work in that conditions. In that condition, you can see in the bottom picture Raymond Davis in 1971 taking a bath in one of the tanks that were shielding the detector from the outside in the mine. After 25 years of hard, difficult work, Davis and collaborators announced that they had managed to catch about 2,000 argon atoms. But this was only about a third of what had been expected in terms of our calculations of the flux of neutrinos coming from nuclear fusion inside the Sun. Where had all the other neutrinos gone? Now, there were two possibilities. Either Davis's experiment was not working as intended, which is possible, a very difficult experiment, or perhaps our calculations of what was going on inside the Sun were incorrect, which was also a possibility. But, of course, there was a third possibility, namely that it was the neutrino themselves being up to some mischief, and in fact, it turns out that this third possibility was the correct one. And that was established by an even bigger detector, the Sudbury Neutrino Observatory, built 2 kilometers underground near Sudbury, Canada, with 1,000 tons of ultra-pure heavy water being water containing a large fraction of molecules with a deuterium nucleus replacing the ordinary hydrogen, whereby deuterium has got 1 proton and 1 neutron as opposed to just 1 proton for ordinary hydrogen. Now, the Sudbury Neutrino Observatory was able to measure simultaneously both the number of electron neutrinos and the total number of neutrinos across the 3 families. And what they discovered was that both Davis' experiment and the theoretical calculations of the expectation of neutrinos from the Sun were correct. Davis had measured the right number of electronic neutrinos, and the total number of neutrinos was compatible with what was expected from theory, which meant that neutrinos, the electronic neutrinos that had been produced at the center of the Sun, had transmutated themselves into the 2 other families upon exiting the dense environment of the Sun. In other words, the 3 neutrino families were not separate families, but they were linked to each other, and neutrinos could change into each other. This disappearing trick, if you like, of neutrinos had profound implications for particle physics, because according to the standard model of particle physics, which was otherwise very successful, neutrinos ought to be massless and ought to stay separate in their own 3 families. But the fact that they mixed with each other, that they transmuted into each other, meant that the mass of the neutrinos had to be non-zero, and also that the standard model of particle physics was fundamentally incomplete. So this was a big realization, and one that led to multiple other activities and experimental research. And the big step forward was taken by the Super Kamiokande detector, which you see in this amazing picture being filled with ultra-pure water. So the Super Kamiokande detector is a huge tank holding 50,000 tons of water. You can see here the little boat with some technicians going around the detectors all around the tank, polishing them and cleaning them before the tank is filled up and prepared for observation. So the Super Kamiokande detector in Japan was able to measure both the electronic neutrinos and the muons neutrinos produced in the atmosphere as cosmic rays, that's to say high energy protons coming from space, hit the atmosphere and produce showers including neutrinos, electronic and muonic. So they found two things. They were puzzled to find that the number of muon, the ratio of muon to electronic neutrinos coming from the atmospheric shower was not as expected by theory, another indication that neutrinos changed family, oscillated, as physicists say. But also they were able to prove that neutrinos produced in the atmosphere above the detector, in particular muon neutrinos produced above the detector, which gave rise to downgoing tracks in the detector, were about double as abundant as muon neutrinos produced from the other side of the Earth in the atmosphere and at the opposite side of the planet, which gave rise to upgoing tracks in the detector. And so the interpretation was that the muon neutrinos produced on the other side of the Earth had transmutated into tau neutrinos en route to the experiment, and this discovery established the fact firmly that neutrinos do change into each other and that neutrinos families are connected. So since then, our understanding of neutrinos has rapidly increased thanks to an increasing number of sophisticated experiments, including experiments where artificial neutrino beams are created at particle accelerators and then detected further down the line, hundreds of thousands of kilometers away, and checked for the composition of those beams, whether new salts of neutrinos have appeared or disappeared from the beam. And over time, neutrinos have become a tool rather than just a mystery or a puzzle. They become a tool for astrophysics and cosmology because neutrinos have a great advantage over other cosmic messengers. They are neutral, so they are not deflected by magnetic fields in the galaxy, and they point back in a straight line to their source. They are also very weakly interacting, which is precisely the characteristic that makes them so difficult to detect. But at the same time, it means they can emerge unscathed from very far away and difficult to reach places in the universe, for example, the core of stars, or jets around black holes, or even the early universe, places that we cannot otherwise see with any other messenger, not light, not cosmic rays, for example. So this diagram shows in black the huge region of distances and energies that neutrinos alone can probe and that are inaccessible both to light or to particle physics colliders. You can see the red vertical line is the limit of energy that we can reach with a Large Hadron Collider, and neutrinos give us access to higher energies in the cosmos that we cannot reproduce on Earth. So the birth of neutrino astronomy can be pinpointed to a very precise moment, the moment when a supernova went off in 1987. This amazing video from the Hubble Space Telescope shows an image taken of the supernova 1987A about 30 years after it went off. So this is an explosion of a blue supergiant star 168,000 light years away from us in the Large Magellanic Cloud. At the time of the explosion, Homo sapiens was still sharing the Earth with the Neanderthals, and it took the light 168,000 years to travel through the universe and get to us. This was the first supernova actually in our vicinity that we could see since the invention of the telescope, since the previous supernova that we could detect in our vicinity was the one of 1604, so-called Kepler supernova, which was much closer and much brighter than the 1987 one. Theoretical models for the supernova explosions had in the meantime been worked out, and they predicted that a large amount of the energy produced by the unbinding of the star would be carried away in the form of neutrinos. And so it was really interesting to be able to see these neutrinos as a new messenger for what was going on in these catastrophic explosions. In fact, it was predicted that about 100,000 billion of billions of neutrinos would pass through the Earth. And so when the supernova was detected on February 23rd, 1987 in the optical, the astronomer Sidney Bludman from the University of Pennsylvania sent a fax. Yes, this was a time when people still sent faxes to the University of Tokyo to his colleagues working on the Kamiokande detector, one of the predecessors of the biggest super Kamiokande, announcing the discovery in really frantically excited terms. And he wrote, "Sensational news! Supernova went off 4 to 7 days ago in Large Magellanic Cloud. Can you see it? This is what we've been waiting 350 years for." And in fact, well, could they see it? They went and fetched the magnetic tapes that recorded the events of the detector. This was a time before the World Wide Web was invented, so yes, they still had physical magnetic tapes that they needed to look at, and they started pouring through hundreds of pages of printouts. And 2 days later, Miss Keiko Hirata, a master student, was the first person to see a neutrino from a supernova explosion when she found a spike in one of the printouts lasting about 13 seconds. And I bet that her heart skipped a beat when she realized what she was looking at. 15 years later, Masatoshi Koshiba, the scientist who directed the group, received a quarter of the share of the Nobel Prize for this discovery. The same signal was also seen by 2 other detectors, and all in all about 24 neutrinos were observed. The fact that they arrived with a range of energies and in a range of times, that the burst lasted about 13 seconds, meant that we could use this data to put constraints on the mass of the neutrinos. Because if the neutrinos had been massless, they would all have been traveling at exactly the same speed, the speed of light, and they would have all arrived exactly the same time, but they didn't. They arrived 13 seconds apart, and that could be translated into an upper limit on the mass, which was found to be smaller than 50 millionth of the mass of an electron. And also the fact that we had seen those neutrinos at all allowed us to put constraints and investigate more in detail the supernova explosion models that had predicted them. In other words, the era of neutrino astronomy had begun. Today, neutrinos are a powerful tool in the astrophysicist toolbox. They are helping us investigate dark matter, they are revealing new, unexpected phenomena in the high-energy universe, and they might even hold the key to some of the deepest secrets of the Big Bang. Now, dark matter has long been a puzzle for astronomers and physicists ever since its gravitational presence was discovered in the 1930s and confirmed ever since in greater and greater detail. We now know that there is about 5 times more dark matter than normal matter in the universe, but we are still completely in the dark as to what it is actually made of. We know it has to be neutral, it has to be massive, and there has to be a great deal of it to explain the gravitational effects that we see in many, many systems in the cosmos. So, neutrinos being neutral and massive were initially a perfect candidate to explain dark matter. Could it be that the relic neutrinos, the ones that were produced in the Big Bang itself, could be the missing part of the universe that we call dark matter? In fact, there are about 336 neutrinos per centimeter cube from the Big Bang, and so if those particles have got sufficient mass, maybe they could be the dark matter in the universe. Unfortunately, it was rapidly realized that neutrinos could not account for the majority of the dark matter, and this for 2 reasons. The first was that laboratory particle experiments on Earth were able to put a limit on the mass of the neutrinos themselves, and that limit, when translated, meant that neutrinos could only make up at most 10% of the dark matter of the universe. The second reason is that neutrinos are not the right kind of dark matter, it turns out. The fact is that neutrinos travel very, very fast, if not at the speed of light, almost at the speed of light. And that has got an impact in the way structures and galaxies form in the universe. You see in the bottom picture to the left a simulation of the dark matter distribution in the universe if the dark matter is assumed to be made of neutrinos, as compared in the middle to a picture of the distribution of the dark matter when the dark matter is a much heavier particle, a particle perhaps 1,000 times as heavy as a proton. You can see that on the left-hand side, the structures that are created by neutrino dark matter are much more diluted. There is less concentration of filaments and blobs, and that's because neutrinos being so fast, they wash out the structure and prevent the dark matter to collapse onto itself under the influence of gravity. This means that galaxy formation is changed as well, and while we do not see the dark matter in the universe, we believe the galaxies form in regions of high dark matter density, and so by looking at the location of galaxies in the universe, we can guess the underlying dark matter distribution. The right-hand side picture shows the distribution of galaxies in our universe, and maybe you can guess that the filamentary structure that is seen in the real data on the right-hand side is in much better agreement with expectations from dark matter filaments in the middle plot, made of heavy particles, rather than filaments made of neutrinos, which is the left plot. In other words, neutrinos are the wrong type of dark matter, so-called hot dark matter, not in agreement with what we see in the galaxy formation data from the sky. So neutrinos perhaps, cannot, while they cannot explain dark matter by themselves, perhaps can still be helpful in our quest to detect dark matter. And one clever way of doing that is to look for dark matter in the sun. The sun sweeps through a dark matter halo in the galaxy as it revolves around the galactic center, and in doing so, it's expected to accumulate dark matter particles in its core over time. So dark matter gets sort of vacuumed up by the sun by gravitational interaction, and over time it will sink at the center of the sun, where it sits in a spot of high density. And the same is true for the Earth, but in much smaller measure, because the Earth has got such a smaller mass compared to the sun, and also a smaller dimension. But the point is that if under some theoretical scenarios, the sun has got a core of dark matter which annihilates, and in the process will produce other particles, including photons and neutrinos. All of the other particles do not escape the sun's core because they are trapped in there by the surrounding plasma. But neutrinos, of course, being so weakly interacting, can and do escape the surface of the sun and propagate to the Earth, where our best instrument to catch them is the Ice Cube Neutrino Observatory in Antarctica. This is a fantastic facility which uses the Antarctic ice cap as a detector medium, mostly for muon neutrinos, in this case from the sun. The Ice Cube detector is in fact a string of photomultipliers, that's to say detectors that look for light, buried between 1.5 and 2.5 kilometers in the Antarctic ice cap, where the ice is very, very clear, very, very pure, and it's a perfect detection medium which replaces the heavy water or the ultra-pure water or the chlorine-based fluid of previous generations of detectors. Now, in fact, these 86 strings of photomultipliers encompass a kilometer cube of ice, which is equivalent to 1 billion tons of ice, 20 times bigger than even the Super Kamiokande detector that we saw earlier. So it's a fantastic instrument which looks at the ice and, like this movie shows, awaits the moment when a neutrino comes in, hopefully from the center of the sun, having been produced by dark matter annihilation in there. A high-energy muon neutrino will produce a muon that travels forward in ice at a speed that exceeds the speed of light in ice, about 200,000 kilometers per second. When that happens, the light equivalent of a sonic boom happens. That's to say, a cone of blue light called Cherenkov light is produced as the particle traverses the ice faster than the speed of light, accumulating excitations along its path, and these excitations do not have time to get out of the way before the muon traverses the ice, and therefore they accumulate on top of each other and give off a flash of light called Cherenkov light. And this is what the photomultiplier of the Ice Cube detector look for. Now, the Ice Cube hasn't turned out turned out any evidence for dark matter so far, but the fact that we haven't seen such events allows us to put limits on the properties of dark matter inside the Sun. After sitting through hundreds of thousands of atmospheric neutrinos produced locally by incoming cosmic rays in the atmosphere above the detector or on the other side of the Earth, the ice cube detector has identified 28 neutrinos, which had a much larger energy than anything else that we've seen before. No known mechanism exists in the universe to explain this kind of high energy particles, which are over 1,000 times higher energy than anything we can produce on Earth, for example, at the Large Hadron Collider at CERN. The only possible explanation, perhaps, is the gargantuan particle jets that are produced when black holes in distant galaxies eat up stars and other materials all around them. So the continuing study of these high-energy neutrinos will open up new windows on our understanding of high-energy astrophysics in otherwise inaccessible parts of the cosmos. And neutrinos can also be used to test the physics of the very first moments of life of our universe, 1 second after the Big Bang. When we look back in time and further out in space, we can, using light, we come to a point where we reach the absolute ultimate limit of visibility of the universe. That's the point when the cosmic microwave background was produced 380,000 years after the Big Bang. We can now observe these cosmic microwave background photons with very high accuracy using dedicated telescopes on Earth and in space. And we can map out the characteristics of this very old light in a very useful way for fundamental physics. But what we can only do in a limited way is to go back even further in time, before 380,000 years after the Big Bang, because during that epoch, photons could not propagate. They were scattered by the hot plasma that filled the universe in the early times. Neutrinos, though, being only weakly interacting, did not have this limitation, and in fact neutrinos were emitted much earlier in time, rather not 380,000 years after the Big Bang, but rather just a second after the Big Bang. So if we could only detect these cosmic neutrinos, then we could perhaps go back in time to the very, very beginning and have an observational probe of the very first second of life of the universe. Now, these cosmic neutrinos are incredibly difficult to detect. They are very, very low energy, very low temperature, just 2 degrees Kelvin above absolute zero. They are all around us, but it was long thought that we could not develop any useful technology to see them. This is now changing in the hope that new technological advances can be used to actually detect this neutrino background directly. And the idea is to exploit 2D graphene layers covered with tritium to do the trick. Now, tritium is a radioactive isotope of hydrogen, which is used in nuclear weapons, among other things. It's also used as a luminescent medium. And we need about 100 grams of tritium to build such a neutrino detector, which is not an incredible amount. Nuclear weapons production in the US alone since the 1950s is in the order of hundreds of kilograms. So 100 grams is a feasible amount if we can build such a detector. In the meantime, we can look for the impact of these cosmological neutrinos onto the cosmic microwave background, the photons released 380,000 years after the Big Bang. And in this simulation from a few years ago, when myself and collaborators looked at this problem of using the microwave background photons to detect indirectly the cosmic neutrino background, you can see the difference that the presence of cosmic neutrinos makes on the temperature differences, which are the colors in this picture of the cosmological photons, the cosmic microwave background. So it was possible back then, and it is possible now, to detect the cosmological neutrino background by looking at the photons released 380,000 years after the Big Bang. Indirect evidence, but evidence nevertheless. In conclusion, almost a century after Pauli first dreamt it up, the neutrino still hasn't revealed all of its secrets. Many open questions remain. What is the mass of the neutrino? Are neutrinos and antineutrinos the same particle, like Ettore Majorana predicted in 1937, before disappearing himself in mysterious circumstances in 1938? Where do the ultra-high energy neutrinos seen by IceCube come from? Can neutrinos help us discover dark matter? And do relic neutrinos hold the key to the secrets of the Big Bang itself?